directly connecting A and B, or zero link. So there will be no more than one link connecting A and B. So these are the simple assumptions. And I want to show the beauty of this algorithm because it's all based on this simple chart. Because when you learn this algorithm, they may tell you this algorithm is called label correcting algorithm or Dijkstra's algorithm. But if you understand this simple graph, you understand this algorithm. Okay. What does this mean? We have three nodes, A, B, and C. And we know that from A to B is 5. The weight is 5. From A to C is 5. A to B is 6. And we don't know any connection between them. So we don't know the weight from B to C, and we don't know the weight from C to B. But from this limited information, we can already conclude something. And what's this? If A is the starting point, we can now confidently conclude that AC will be in the shortest path tree. Because no matter how big these weights are, you will always take more than 6 to go to C, because all the weights are positive, right? Is it very obvious? If you understand this, you will later understand Dijkstra's algorithm. Actually, it's only a little more complex than this. So let's think about this thing. A is the start node. And we know that AC, AB, and AD are part of the shortest path tree. And I use a triangle to mark this area. So let me say that again. We know of shortest path tree, AC, AB, and AD. And then we already, because according to this AC, AB, and AD shortest path tree, we can get the direct weight from A to CJ, ACI, ABI, and ABH, and so on. These blue links, these light blue links, are representing the links that can be directly connected to the shortest path tree. And the black ones are representing the links that can currently not be touched. Okay, let me say that again. This shortest path tree, the blue links are the links that have connection to the shortest path tree. And the black ones are the ones we are not caring about at this moment.
Why AE is not the right one?
Because at this time, we only explored this area, and we have only created this shortest path tree. I'm not saying AE is not the shortest path, but I have just created this thing. This is unknown. AE is unknown. Because we are doing this one by one node by node. We have created two sets of nodes. The one set is the nodes that are belonging to the shortest path tree. The other set is containing all other nodes. So two sets. One set is in the shortest path tree. The other set contains all other nodes. And currently we have A, B, C, D in the first set. And the second set includes others. To show it easily, I modify this graph using this graph. So you can see it. So from A to B, A to D, and to C. See that? And we have E, which is directly connected to A. And we have these links. So I just organize the graph so you can see it easily. And here, given that the shortest path tree here, and we know that AE is less than ACE. I mean, for this assumption too, we are just comparing the distance from the start point to each adjacent node using this tree. So from A to E, using this shortest path tree, there can be two paths, AE or ACE, right? And we know that from the calculation we previously done, we already know AE is less than ACE. And similarly, we know ABH is less than ADH. So these dotted lines are representing the links that are already discarded according to previous calculation. So if we know ACE is shorter than AE, then we deleted this AE. We know ABH is shorter than ADH, then we deleted ADH. Similarly, we know ACI is less longer than ABI, so we remove this ABI. Be very careful, we are comparing ACI and ABI, not CI and BI. It is that. After this comparison, we now have the shortest path, the current shortest path from the starting point, using all the points in the shortest path tree to any adjacent point. So I have from A to E, A to F. F is not touched by this moment. A to E. We have A to H. We have A to I. We have A to J. In another, correct? Yes. So let me say that again. I have the distance from A to E by ACE, and A to H by ABH, A to I by ACI, and A to J by ACJ. So it's already a lot of time. And here is the third thing I know. By comparing this distance from A to E, H, I, J, I find that ACI is shorter than AE or ADG. Sorry. So let me say that ACE is less than AE. So ACI is less than ACE or ADG, ABH, and ACJ. And what can we conclude from this point at this time? What can we conclude from these three conditions? We can confidently say ACI will be the shortest path. I should be selected in the shortest path tree. And the reason of that is the same as if you take a look at the previous case. Let's look at this again so you understand that. If AC is shorter than AB, then no matter how long this link is, AC will be the shortest path. And in this case, we know ACI is shorter than ACE or ADG or something else. Then no matter how they are connected, for example, if ACI is not the shortest path, then there must be another shortest path called A something I. But A something I has to be consisting of either ACE or ADG, ABJ or ACJ, right? Otherwise, it's impossible because these are the only connections to the outside. So if you don't go through ACI, you have to go through ACE or ADG or ABH or ACJ. And these are already longer than ACI. So those paths can only be longer than ACI. Do you understand this? This is the most important thing I want to talk about today. So to summarize, we have a shortest path tree. And we already, according to the shortest path tree, we have some adjacent nodes. And we already know the shortest path from the starting node to any adjacent node. Then we conclude that the shortest path from A to the adjacent node will be one shortest path, and that adjacent node can be selected into the shortest path tree. So I'm comparing ACI, ACE, ABG, ABH, AC, ACJ, comparing from between A among A to any other adjacent point. So I'm using a lot of time talking about this, and I hope you understand. Do you have any question about this? Are you really clear about that?
How do you construct a shortest path tree? How many nodes should you explore? Initial shortest path tree.
So in Dijkstra's algorithm, we are always looking for the next shortest path. The next shortest path. So for example, we want to explore from A to B. Then we start from A, and we explore the shortest path one by one until I find the path directly from A to B. Okay, so in this case, we can conclude that ACI is the shortest path. And then we put I to the set 1, to the set of shortest path nodes. And then what should we do? After this, we have to upgrade the shortest path from this tree to adjacent nodes. In this example, if I put this node into node 1, into the shortest path node set, then I have to consider if IH or IJ can be used to access H and J. So previously we have a shortest path ABH. Now we have a new node called I. We have to consider if ABH is shorter than ABI.